The vacancy concentration in a crystal doubles upon increasing the temperature from 27 degrees centigrade to 127 degrees centigrade. It means when we are increasing the temperature from 300 Kelvin to 400 Kelvin, the vacancy concentration in a crystal is getting doubled. The enthalpy, that is in kilojoule per mole of vacancy formation is. Okay, so it is asking me about the value of QV. Okay, that is the enthalpy of vacancy formation. So let me write the first formula, that is NV equal to N into e to the power minus QV by KT. Okay, this NV basically is the number of vacancies at equilibrium, that is equilibrium number of vacancies. This N is the total number of atomic sites. Okay, this QV, this one QV is the energy required for the formation of vacancies. Okay, this K is Boltzmann constant and this temperature T is temperature in Kelvin. But the enthalpy they are asking in kilojoule per mole. Okay, but in this formula, since it is KT, okay, this will give me the QV value in kilojoule per atom. So to convert this into kilojoule per mole, I have to replace this K with R. Okay, for per mole I will use R, for per atom I will use K. Okay, so it will now become NV equal to N into e to the power minus QV by RT. Yes. Now the vacancy concentration is doubling, okay, when we are increasing the temperature from 27 to 127. So we can say NV at 127 degree, that is 400 Kelvin, divided by NV at 300 Kelvin, that is 27 degrees centigrade, will be equal to what? Equilibrium, sorry, this is the total number of atomic sites into e to the power minus QV by R into T. Temperature is how much? 400 Kelvin. And in the denominator, it will be N into e to the power minus QV by R into T, that is 300. Okay. Now N will be cancelled out. And you know, this ratio is given to you, that is 2 equal to e to the power minus QV by 400R, and this will be minus minus plus QV by 300R. If you take ln both side, natural log if you take, then it will become ln2 equal to QV by 300R minus QV by 400R. Okay. Now if you proceed further, ln2 is 0.693. Okay. Now we can take QV by R as common, so it will be 1 by 300 minus 1 by 400. Now 0.693 equal to QB by R. This value will be 100 by 1200000. So QB will be equal to, and what is the QB? This is the energy or enthalpy that is required for the formation of vacancies. So formation of, 1 mole of the vacancies, because we have to find per mole here. So it will be equal to what? 0.693 into R. Okay, it will be cancelled out, so it will be 1200. Now in the question, the value of R is given, that is universal gas constant, that is 8.314 joule per mole per Kelvin. So it will be 0.693 into 8.314 into 1200. That will be in joule per mole. Okay, and then we have to just multiply it. Okay, after multiplication, I will be getting approximately 6914 kilojoule per mole. Now this is in joule, so multiplication I will get in joule, I'm sorry, this is in joule per mole. Now since they are asking in kilojoule per mole, so we have to further divide by 1000. So this much kilojoule per mole will be the value of enthalpy of vacancy formation. And if we round off to two decimal places, it will be 6.91 kilojoule per mole. So this is the final answer for this question. This question has been asked in GATE Metallurgy 2021. Okay. So once again, that is very simple here. This is the total number of vacancies at equilibrium. This is the total number of atomic sites into e to the power minus qb by kt. This is qb is energy required for the formation of a vacancy. Okay. For vacancy, I have to use here k. For 1 mole of vacancy, I have to use here r. Okay, because k multiplied with the Avogadro number is giving you r value. Now, since in the question it is asking you kilojoule per mole, so better to use r. Okay. Now all the value were given that it was saying that vacancy at 400 Kelvin is just double as that of 300 Kelvin. Then I have used this equation 2 times and I have divided and got the final value of QV. So this is the enthalpy or the energy of vacancy formation per mole, that is 6.91. Okay. So this is your final answer.